young people graduate and then move along. So when Sridhar was just graduating from Cornell, he was bubbling with ideas and he was ready to conquer the world. He was really great discussing things with him and all that. And what I see is all of us start thinking we are going to conquer the world, but then only few achieves. And in my opinion, Sridhar has done extremely well. He's one of the most achieved in operations management, operation research, and he has been a successful entrepreneur. He started two very successful companies, SmartOps and Organ. And just to tell, I even got call from SmartOps asking whether I would like to join SmartOps. They were trying to recruit. So it was nice to see how successful he has been. But what was more amazing is that he's making serious inroads into quantum computing. I think in that field, he's making a severe impact, because I have had contacts from people at Berkeley and Cornell and other places, and they all praise him in terms of the type of contribution he's making. So I'm actually very proud. I actually wrote to Sridhar saying that I am proud that he is from the OM area, so that I can boast about how one of our guys can do great things, not only just in our OM, but in other fields. So I'm excited to have Sridhar give this tutorial, and I'm looking forward to listening to what he has to say. Thank you, Sridhar.
Thank you, George, for the kind introduction. Do I have share screen now?
You should be able to.
Yep, I do. Thank you. How is the screen?
Good.
All right. Thank you all for coming, and thank you, George, for inviting. I thought I would go through several slides and answer some of the many questions that you may have. And let's see if we can make it somewhat interactive. So people should, raise hands or speak up so that we can keep it relatively interactive. I think everybody is bored with Zoom webinars. So let's see if we can keep this, interesting. So let me move ahead. Oops. So let me start by listing a lot of collaborators. At Tepper, in 2018, I recruited two postdocs. One is Hedayat Al-Ghazi, PhD in EE. He was working for a company called 1Qubit in Canada. And Raouf Dridi, who's a PhD in mathematics from France. And he was also working at 1Qubit. And they were both interested in doing something new. And when I said I'm interested in creating postdoc opportunities in a business school for practical use of quantum computing, they decided to join me. Since then, a PhD student in the chemical engineering, David Bernal, who will be joining Purdue actually in chemical engineering in the fall. His thesis defense is this afternoon at 3 p.m. He has a job offer from Purdue Chemical Engineering, and I think he'll defer it for 2 years and do a postdoc at NASA or somewhere else, but he will be joining Purdue. And part of his thesis is on quantum computing. And so this is the spread of quantum computing from Carnegie Mellon into other universities. Vikesh Sidhu has his PhD in theoretical physics from CMU. His advisor is Bob Griffiths. If you go and see, he has won many prizes that Murray Gell-Mann and Feynman and Subramaniam Chandrasekhar have won. And he's periodically listed as a Nobel candidate if Foundations in Quantum Mechanics ever comes back to life. And Sidhu Vikesh did a postdoc with me and is now at Gila. Rauf Brady joined a startup called QCI after the postdoc, and Hedayat Al-Legacy is now at IBM Quantum doing quantum finance. So this is how I created the group. So I think some of you had questions about how did it get started. It got started when I hired physics, math, and EE PhDs as postdocs. Then NASA had sent out a RFI that said that they will give 100 hours of D-Wave computer for free if we could write a proposal. And so I wrote a 4-page proposal saying that I would like to explore the use of D-Wave to solve combinatorial problems that arise in business. I think I was the first and only business person to ever submit over there. Most people are chemistry folks and so on and so forth. And so out of, I think, surprise, amusement, etc., they gave me the access. It has been a wonderful collaboration. They actually have funded my teaching. I'll talk a little bit about that. We have worked on papers together. They took David as an internship candidate at NASA Quantum AI Lab. And it has been a very nice collaboration that I'm hoping to continue for years to come. I'm an alum from IIT Madras. And so I wrote to the director there and said, does somebody at IIT kind of do this quantum thingy? And it turns out, yes. India is taking quantum seriously, and IIT Madras is one of the centers of excellence. They have a new master's program, 3+2. In quantum science and technology funded by the Indian government. And so Anil Prabhakar, who's a EE professor, got his PhD from CMU. And then Prabha has her PhD from Caltech in physics from the very, very top man in quantum information science, John Preskill. So John Preskill is probably the most famous quantum information science professor. He's the Richard Feynman Professor of Theoretical Physics at Caltech, and she is his student. So Prabha, Anil, and I have been collaborating on things, and they actually mirrored the course I taught here at CMU at IIT Madras, and we will be repeating it again. Then I have a blog that not many people read, but it turns out some Russian physicists, as well as some Stanford Cornell physicists, have started to read it. And so I got an inbound inquiry from Cornell. Peter McMahon, if you go and check his Google Scholars, the young assistant professor, he has got a couple of science and nature papers already. And I think his first nature paper probably has more than 2,000 citations within the first 6 months. Created something called the coherent icing machine that I'll bring up later. And he texted me to say, emailed me and said, hey, I'm finishing my postdoc at Stanford, EE, going to Cornell. I noticed what you're doing. Maybe we can collaborate. So I'll tell you a little bit about that. And then Amazon actually has an NSF interaction where they said that they will provide free Amazon bracket access to researchers with NSF grants. And so David and his advisor, Ignacio Grossman, and I wrote an add-on proposal. And that's how we got hooked up with Amazon. And Amazon not only gave us free access, they liked the quantum integer programming class that I was teaching so much that they doubled it for student use. And obviously students took courses, the course here at CMU, and then also repeated over there. So I want to show you kind of this ecosystem that I'm building. And as you can see, that pretty much physics, EE, math, computer science crap. Okay, and so I'm trying to basically get OR and OM in there. So hopefully it gives you a sense of how this is happening. The course is 47,779. Towards the end of the presentation, I'll give you the GitHub link. It has all the slides. It has the videos. It also has Python Colab notebook if you want to cut and paste code that you can use, and then if you have Amazon bracket account, actually do quantum computing. So I also am making this an open source lecture and code so that the barrier to entry is kind of minimized. Okay, so a little bit of the kind of the background here, and now I think an expectation that there is an agenda. There is an agenda. So I'll give you an orientation. You had asked me about the hype versus reality. I want to attack that first, Manmohan. And I want to tell you the focus of the research and teaching I'm doing, and limit the presentation here to that part of quantum computing that I'm most involved in. There's a lot of vocabulary, and so I have tried to keep the minimum. So I will spend some time on the vocabulary because this is an entirely different language, really, from what we are used to. The substantive portion of the content will be on an algorithm that we created here called Gamma, Graver Augmented Multi-Seed Algorithm. I will show some results on D-Wave, show its limitations and strengths, show a classical algorithm inspired by it and its performance, and then close with what I think unconventional computing can be, room temperature computing can be, poor man's Eisen can be, and discuss what the 21st century might look like. Okay, so that's kind of the agenda. Any questions so far, George or Manmohan? Since it's a small group, we can be more interactive.
That's good. Yeah.
So George mentioned, what I really like to do in life is solve real problems using cool math. That's what I like to do. And I found operations research and operations management to provide me that vehicle to do it. You probably have or have not seen a 2017 MSOM forum article I wrote, an essay on operations management where I talk about that. I think Socrates said that he wants to die knowing one more thing. I would like to die doing one more application with one more kind of math. Okay, so at the end, I want somebody to say, I can't imagine that he actually wrote K papers with K different types of mathematics, and hopefully, some square root of K plus applications. I have done extreme things like being a consultant to the firm and executive education guy for McKinsey, which I don't consider academic. I've done practical things directly with Fortune 500 companies. I have some startups and working with other startups. Everybody does healthcare, so I have some work on healthcare. And on the left, you can see the variety of mathematics that I have explored over the years. So what I really enjoy is finding a new application or a new math and saying, can I learn it? Can I manipulate it? Can I extend it? Can I adapt it? Can I have fun with it? And that's pretty much kind of a summary of my professional life. I think George mentioned that my 2015 plenary talk in POMS was called Why I'm an Academic Catalyst. It turns out that in the beginning, people raised their eyebrows, but in 2017, when I was elected to the National Academy of Engineering, this was the citation. I mean, this citation basically said, we're electing you to the National Academy for being you. I mean, look, being elected to the National Academy is fun, okay? But to be elected for exactly who you are, come on, that's priceless, right? And so I was very happy that the community actually recognized the fact that I am involved in the developing, but I also am involved in the commercialization of this, okay? Some of the companies that use SmartOps are down there as part of SAP Integrated Business Planning. I think right now 700 companies in 50 countries use it. So the world supply chains run basically off the code that many of my engineers wrote here at SmartOps. So now, Manmohan, what next? So I said, what can quantum computing do to nonlinear integer optimization? And what can integer programming do for quantum computing? Today, I don't have time to talk about the second piece, so I'll only talk about the first piece, okay? What can quantum computing do for us, okay? I consider we are the users, right? We have hard problems to solve. There are people claiming there is a new gizmo called quantum computing. I'm saying, okay, what can you do for me, right? the promise of quantum speedup can essentially be summarized to these two things. There's something called unstructured search, which means you have a database, there's no structure, and you have to find what you're looking for. And classically, if you check, it is order n over 2. It's order n, right?
Yeah.
Right? There's no surprise.
Yeah.
Grover in 1994, Lou Grover at Bell Labs wrote a remarkable algorithm for quantum, where he showed that by superposition and a certain kind of operation, which is reflection and rotation, which happens in quantum space, you can find the answer with probability 1 in order root n. Okay, that was presented in Soda and all that kind of stuff, and became kind of the first big famous paper in quantum computing in 1994, 1995. Okay, that's Grover search. Okay, essentially it means that if a call to the oracle is 1 second, and classically you need to do 36 times 60 times 60 calls to do something, then Grover algorithm will take it down to 6 minutes. And you say, I think I just woke up. Then came Peter Shor, who was also at Bell Labs and now is, I think, chair professor at MIT, has pretty much started winning all the awards after many years. Most recent, I think, was the Dirac Prize, which is the highest prize given in theoretical physics, actually. And he's probably the first computer scientist or mathematician to win the Dirac Prize, because usually you're like, a real physicist, and Dirac to Nobel is like almost there. Okay, and he showed that prime factorization can be done in polynomial time. Okay, and so this started the world of quantum cryptography and all the craziness that we see so far. Okay, so if there are two things you need to learn about what happened that got quantum computing to mainstream interest, why DoD is paying a lot of money. And I joke about this, even Donald Trump, who's famously anti-science, actually allocated $1 billion for quantum. So, quantum certainly has gotten the hype that this one brings up. Okay. There are two major buckets of hardware. One is called adiabatic quantum computing, sometimes called quantum annealing, that D-Wave and Honeywell are doing. And a second one, which is very similar to the logic gate models that we're used to, called the gate circuit models, obviously with quantum logic and not classical Boolean logic, is being followed by IBM, Google, and Rigetti. So a big picture here is to say there are different paths, just like Blu-ray and VHS. There are AQC and gate circuit models, and it's not clear who is going to win. Okay. So when you hear people fighting between D-Wave and IBM, they're basically taken two different paths. There are two more paths called topological quantum computer that Microsoft wants to do. And then there is something called MCBC, I forget the name, it's like not on the top of my head, which is very, very theoretical, but these two are the big buckets. Okay, these guys actually have hardware that you can touch it.
Sridhar, do they make any claims on which is faster for a given problem with the given technology? Just speed, no other advantage.
Yeah, Google has claimed a certain speed up on generating random numbers, which was probably the front page news of 2018. Other than that, I think people are just still publishing papers trying to one up each other, and I don't think the community has chosen a winner.
Okay.
This is what the chip looks like. Okay, if you look at the D-Wave and you say, what is happening? You're going to see these dots. They are qubits, and I'll come to that in just a bit. They are spins. Okay, I'll come to that in a little bit. So these are language you need to know. Qubits, spins, and they're coupled. You see the things there. So you need to know something called couples, and you can entangle them. And so quantum computing is about manipulating superposition spins that are entangled to do things that classical computer cannot do. Okay, so that's like the single sentence difference between the two. But there are a lot of words out there, so just hang in, and I'll tell you what some of these words are in just a bit. Okay, no pun intended on the bit. This is how the IBM circuit looks like, and this is a gate circuit model. Okay. So the hype is this business of quantum supremacy. Okay, they actually got into trouble for naming it quantum supremacy because it seems like white supremacy and so on and so forth. So they dodged that bullet, but they're still called quantum supremacy. So I think that's hype. The quantum computer is not going to solve all problems better than classical computer. That is not going to happen. Okay, I think people have backed off from it, and so now they're very, very narrow to say for the specific class of problems, I believe quantum will be better than classical. Okay, so I think the hype you might have heard about, oh my God, the quantum computer is coming, the whole world's going to change. That is clearly, a hype. Okay, but what is reality is that you can do the best of both. You can say, let me take advantage of 50 years of classical algorithm development and add on the quantum as a supercharger as need be. And even more interestingly, you start thinking differently about classical algorithms if you say, oh, I've now learned some physics I did not know before. So I want to show you an hybrid quantum classical algorithm that we created and running on D-Wave, which has attracted attention, as George mentioned. And then a quantum-inspired fully classical algorithm that currently will do 100 times faster than Gurobi on specific structured problems. Okay, so this is the contribution of the Tepper quantum computing group, starting from Hidayat and Rauf and David. So what I want to bring to the table is I am not a hardware guy, right? I'm not going to go and change the qubit noise parameters of an IBM machine. That's not what I'm doing. I'm saying when you improve the qubit noise and improve the connectivity and improve the number of qubits, I want to know, can you solve a problem better than the problem, say, a classical algorithm that I may be using? And if so, how much better, right?
Sridhar, can I interrupt you?
Sure.
At this level, where the slide was that you could do hybrid quantum algorithms, at this level, do I need to know that there is adiabatic or gate computers, or I can ignore that and the language?
No, you cannot. The algorithm for D-Wave will be using something called quadratic unconstrained binary optimizer. I'll come to that, something called a QUBO.
Okay.
While for a gate circuit algorithm, you have to write a circuit. Now, consultants and IBM has come out and said, don't worry about it. Why don't you just send me your Cplex code and I will take care of it? So they are basically saying, if you are somebody who is using Cplex or Gurobi and you want to know how to use IBM machine, let us worry about how to convert that into a circuit, right? But if you had to do it yourself, you'll have to figure out how to write the algorithm in a circuit, which is much more difficult, and the machines are far less capable than writing it in the form of QUBO, which I'll tell you is relatively straightforward and directly applicable not only to D-Wave, but for other physics-inspired Ising solvers, which are available in the market today, and which is the path I'll be taking. So I would say for our community, learning how to use the D-Wave Ising solvers using quadratic unconstrained binary optimizer is the best path.
Okay. Thank you.
Good question. Yeah. Interestingly, 99% of courses are taught in gate circuit model. You go to Coursera, go to MIT, go to Stanford, free stuff. They're all talking about gate circuit models because they're taught by theoretical computer scientists who have no interest or desire to solve a practical problem. So I also think our community has the advantage of saying, we actually want computational results. I want to press a button and solve a larger problem in the same time, or the same problem in a much faster time, or some combination thereof, right? So you'll see that I'm taking a very computational approach, which is pretty much what I did even in my inventory research. As you know, I wrote some stochastic dynamic programming papers, which everyone has to do, and say Carl Lin was a smart guy and all that. But really, the usefulness came from my work in IPA, which was very scalable, perturbation analysis, which I then, created a, even faster algorithm, for SmartOps. So I don't think anybody actually solves, Clark and Scarf the Clark and Scarf way. I mean, it's not doable. So here's some vocabulary. Superposition means that you can be in 0 and 1 at the same time. This is a quintessentially, the opening 4 things are quintessentially quantum. It has no classical counterpart, right? In a bit, you're either a 0 or 1, but the mathematics of quantum computing allows you to have a mathematical structure where you are alpha times 0 and 1 minus alpha times 1, where alpha is a complex number. So one thing you will notice is when you go to quantum mechanics, you are in complex space. Square root of -1 is everything, okay? The second thing is it's an amazing thing called spin. First of all, it's badly named because it's not like Earth rotating, because electron has spin, electron is a point. So what is it spinning about? That's not what they mean. What they're saying is it has a magnetic moment, but it can take only 2 values up and down. And so what people do is to take a physical thing that has a spin and make it, the qubit, that is used in these machines. Now, while IBM and Rigetti and Google are all gate circuit models and they have the same logic, the specific qubit that they do are maybe different. Okay? Entanglement is a whole different thing that even Einstein fought for decades and eventually is wrong about it. And so what you need from quantum mechanics is that we're dealing in complex space. We're dealing with superpositions of 0 1s. Our algorithms will manipulate the superpositions until the very end. We'll take a measurement. With some probability, you'll get a 0. With some probability, you'll get a 1. And that is a randomized algorithm. So quantum algorithms are randomized through superposition manipulations in complex domain. That is the mathematics of it. A specific model that has been of tremendous importance to us is called the Ising model. Started by a guy called Ising, who was a PhD, was advisor of a student Lenz, Ising Lenz, or the other way around. Until the Ising model, magnetism was not explained. So the Greeks found magnets in 400 BC. The Indians found magnets in 600 BC. In those days they're fighting bows and arrows and all that. And if the arrow went in, they would put the stone and the arrow would come out because they knew the magnetic things. If you read the Siddhartha Brahmanas and all that, the use of magnets in war is kind of well known in healing and so on and so forth. But nobody knew actually until 1925 how magnets work. In fact, it was proved that classical physics cannot explain magnetism. So the Ising model is the base of fundamental magnetic storage and physics and so on and so forth. In my view, this should be taught in high school. Spin and magnetism should be taught in high school, STEM, if not core engineering undergrads, and not relegated to quantum physics anymore. Okay, and so central to adiabatic quantum computing, central to this way of quantum computing is the Ising model. And what I have done is map operations research into Ising model and said, I have all this physics now to take advantage. Okay, so that's what's happening. And the purple part is really, kind of the vocabulary from the physics side. Okay. The second part, a quadratic unconstrained binary optimization. Binary means 0, 1 variables. Unconstrained means unconstrained, there are no constraints. Quadratic means the objective function is of the form x1, x2 plus x1, x3 like that, okay? So the input into an Ising model is a cubo, as I'll show in just a bit. So whatever objective function you have, you need to make it into a cubo, okay? That's the part we need to learn, which is not very hard to do, and I'll show it, okay? Now, there's a third piece which operations research people might not know, but is actually part of math programming theory, called test sets. Okay, most of us, when given an integer program, will take a linear relaxation, do branch and bound, branch and cut, blah, blah, blah. That is, we get off the lattice and then try to get back on the lattice, right? That's kind of what we teach people, right? And I've always hated that, although I've used it practically and made money from it. I just felt intellectually, you should not leave the lattice. It turns out there were mathematicians who did not leave the lattice. Jack Graver being one of them. And so there's something called Graver basis, where you are on a lattice and you're an interior point walk only on the lattice. Every step is an improvement, and when you cannot improve anymore, you're guaranteed optimal. And therefore, this is there in theory, but it is so theoretical and so impractical that even Gerard Cornejos, who's a math of OR guy, who won his second Lanchester Prize in integer programming book, felt it was so theoretical, he spent only half a paragraph on it, called the primal method. That is, what I'm saying is test set makes math of OR guys look practical. This is like math, okay? And so I said, aha, this is an opportunity to take that math and connect it to Ising and see what I can do. Okay, so just to show you kind of what's going on, and I'll quickly go through some of this stuff. So Ising problem says you are given a grid. You have these things called spins. They're coupled using coupling. They can be positive coupled or negative coupled, Jij. And you let nature decide and find the minimum energy solution. And depending on the Jijs, you get a solution. That is, a quantum algorithm sets up the nature to do it. And nature works at nano speed. Okay, it'll do this. It'll equilibrate in 10 to the power minus 9 seconds. So what we're going to do is to make nature equilibrate 10,000 times 10 to the power minus 9, which is 10 to the power minus 5 seconds, and then get a probabilistic answer. So that's really what is happening. We are going to have nature equilibrate, measure, find the answer, nature equilibrate. That is D-wave. So mentally speaking, we're asking nature, can you please equilibrate in nano speed, in nano time? Okay, and that's really at a very, very high level what is happening. Okay, and I was joking that I've become a big fan of nature now, because if nature can make me money, I'm interested in nature. Okay, so the physical machine looks like that. It's a miserable looking thing. It's huge, and these qubits are all sitting inside in 0.03 Kelvin temperature. So you and I cannot build it at home, for example, and you need hundreds of millions of dollars to build it. So I think that's why we're talking about poor man's machine. And what Amazon has done is you don't need to buy the machine; you just have to pay for fractional use. Okay, I'll come to that in just a little. It's 12:08. I'll just tell you a little bit of what is happening in adiabatic quantum computing. This was a 1928 or 1929 result by von Neumann and others that said that if you start a quantum system in equilibrium and slowly change its Hamiltonian, which is its energy function, then the equilibrium is maintained so that at the end of the change, you are actually in equilibrium of a new Hamiltonian. This is 1929 result with von Neumann and others. Okay. What these guys are saying is, let's start with a baby Hamiltonian where the objective function is something, and all random 0-1s are the optimal solution. Let's start, because that we know. Okay, that's called preparing the initial solution. And then slowly change this initial solution to the problem Hamiltonian. So basically, our problem gets mapped to the Jijs, and it slowly goes from a known solution to a non-problem to the problem that you want, and that is adiabatic quantum computing. Okay, and 10,000 reads in D-wave take 0.3 seconds. Okay, just to give you a sense of how fast nature is, in finding these answers. If you go into physics books, you will see the tensor mathematics, Pauli matrices, and representing Hamiltonians with respect to spins. As a user, you don't need to know it. Okay. For example, to drive a car, you don't need to know the software of anti-locking braking systems. Right? So if you just want to be a user, you don't need to know this. I'm just showing it to you so that if you happen to see it, you know it's like beneath the covers. The theory goes like this. adiabatic quantum computing and gate circuit models are equivalent. That has been proved. Ising model is Turing complete, which means that any problem that you can solve classically in a Turing machine, an Ising model can do it. We're not missing anything. What you see focus in theoretical computer science is something called quantum approximate optimization algorithm called QAOA. Okay, this is what folks are doing, like Peter Shor will be doing this, and this is what theoretical computer science is. Okay, these are the folks at UC Berkeley and Princeton, and you say, who are these folks winning Gödel Prize, and who's in line to win the Turing Prize, and so on and so forth. It's these guys. Okay, they're doing QAOA. It's also shown that QAOA is just a discrete version of this continuous AQC that I mentioned. Okay, so eventually they'll all be equal. I just want to show you that I am taking a position where I am doing adiabatic quantum computing when the majority of the people are doing gate circuit. I am more a guy who uses D-Wave than using IBM. I'm going to solve problems using test sets rather than LP relaxation. I'm interested in computational performance and not in worst case bounds. I'm interested in problems in supply chain and finance and genomics and not in cryptography and quantum chemistry. Okay, this is Sridhar. So here's the algorithm that our group came up with. You have a function f of x, ax equal to b, x is integer, non-negative, and everybody in OR, OM should say, this is the first slide I understand completely. Okay, yes. This is the problem I want to solve. How I solve it is I split it into three pieces. I take the objective function away. I take the constraint. In one, I want to find the kernel. From the kernel, I get something called the test set Graver basis. And then I get a sample of the feasible solutions. From each of those samples of the feasible solutions, I'm going to take a walk with respect to the Graver test sets. When I finish, I am done. Okay, that's the algorithm. That's as simple as that. And the objective function is used to decide, should I take the step or not take the step? Because f of x tells me, right, whether the step is improved or not. That is all the algorithm is. This is the primal algorithm for integer program that Gerard wrote half a page and said, there are primal algorithms based on test sets, thanks to Graver. Let's move on. Okay. And I said, oh, no. I'm going to launch from that point. So you compute Graver, find many initial feasible solutions, and then you do augmentation. The Graver basis is quantum classical because I get the kernel from a quantum, and then I do what is called conformal minimal filtering in a classical way. I get the feasible solutions on quantum, and then I do all the augmentation in a classical way. So that is what I mean by saying this is a hybrid quantum classical algorithm where I'm calling the quantum only to do things that classically you would be crazy to try. Okay. Non-linear integer program. You can start from a feasible solution and move forward. That's called a test set. Graver basis is a test set. You can get from a kernel. The beautiful thing is Graver basis is a test set for a wide variety of objective functions. These are papers written by people like Bernd Stromfeld, who is math department at UC Berkeley and now at Max Planck. What I'm saying is these guys are not even math of OR. This is math. But if you go through, kind of all the pain and suffering of their language, it boils down to this, that you have a lot of objective functions for which the Graver basis is a test set. Okay, and that tells me that it's a good general purpose thing to go. So one of the things that I really focused on when I was developing IPA, perturbation analysis and inventories, and then also building smarter, I want a general purpose scalable algorithm. I don't want to build an assumption specific, problem specific algorithm, and it's not worth it. I want to do one thing and then rip it through, right? That's kind of my modus operandi. A kernel is AX equal to 0. You have to make it binary encoding if you want, or a unary encoding, depending on what you want. So you have AX equal to 0. Now you can take A transpose A, call that matrix Q, then X transpose QX becomes a cubo. That's it. What happens is you look at all the elements, diagonal and off diagonal elements, they become the JIJs for the Ising. Okay, so in a very high level English, you can convert your matrix A into JIJ and tell nature, please equilibrate. That is all that's going on. All you need to know is how to convert the A into the JIJs. Okay, and if you go and look at my lecture notes, I showed step by step, 10 steps to go from A to Q. But now I've also built in the Python code, send A, I will give you the JIJ because it's a program, right? But this is classical, front end. And then you send the JIJ into D-Wave. D-Wave spits out 10,000 samples. You take from there and you continue further. Okay, so that's kind of, you can view D-Wave as a black box, basically, right? But to call it, you need to call it a cubo. And you can't call a gate circuit model with a cubo. To answer your question, Manmohan, you need to call it using something else, okay, using circuits. And that's very, very difficult to do. So, okay, so that's, hopefully that's...
Given a constraint problem with some objective function, can we convert the constraints into using Lagrangian or just using penalties into an objective function? So you just now have a very large objective function, but just one function.
Yeah, so people did that first and found that it doesn't work well.
Okay.
The energy function has such bad values and so on, and the size becomes so big that they're unable to solve even small problems well. And that is why I did this decomposition.
Okay.
So yeah, people did that and it went nowhere. It will go nowhere.
And then the other extreme, just take a satisficing problem. Based on what you're saying, you would get good solutions if it's a pure satisficing problem.
Yeah, you would get.
Okay.
You would get. It's an opportunity.
Mm-hmm.
So let's take a standard capital budgeting problem. You have a reasonably bad objective function. You have AX equal to B. You want to buy some stocks or not. You can have -1 and all that, right? If you want to sell it. There is a mean return. There is a standard deviation, and so on and so forth. So you call D-Wave, and out of the 10,000 calls, it gives you 6,500 unique solutions, right? Because many calls might return the same solution. And then you augment it using the kernel, and it finds the optimal solution. Just to show you, in principle, that's all you're doing, okay? You're getting some feasible solutions, you're walking for a bit and finding the answer, okay? One call is 0.3 seconds. So 0.3 seconds to get 6,500 feasible solutions, 0.3 seconds to get some kernel elements. And partial kernel elements are enough because I have so many feasible solutions. And when I walk, so 0.3 seconds plus 0.3 seconds plus some post-processing second, in about 1 or 2 seconds, I can solve it. Okay. The same paper, I think, was published in OR and so on. And depending on the epsilon and mu's and sigmas and how tight it can take like 45 minutes. Okay. The downside is, I'll come to that in a bit, if you cannot represent the problem on D-Wave because it doesn't have the qubits or it doesn't have the couplings, then you're out of luck. So what happens is, as long as you can represent your problem into their matrix, it's called embedding, classical, you're probably not going to beat you. The problem is the hardware is not ready to be able to embed many of the problems we care about. Okay, so what really happens is what it can solve, it solves very quickly, but without more qubits, without better coupling capabilities, right now, except for a few cases, D-Wave is not going to beat classical best. Okay, because the hardware is not there. But once the hardware comes, they went from 2,000 qubits to 4,000. They claim they're going to go up to 10,000, improve the precision. Suddenly, you'll be like, wait a minute. Click, click. You're going to get the answer. Okay. So is D-Wave usable now to beat what you have programmed? Probably not. But can it beat it in principle? Yes. Can you repurpose D-Wave today as I have done and then beat classical? Yes. Right. But in fact, what I found more useful to do is to say, are there classical problems with special structure, quadratic assignment, quadratic semi-assignment, cardinality Boolean, and so on and so forth, very structured problems for which I don't even need to call D-Wave. I can read off the Graver basis, because cardinality Boolean problem is EI minus EJ, the vectors, unit vectors. Are the Graver basis. So once I got to thinking like, oh, wait a minute, I'm going to do test sets. I'm going to convert it into an Ising model, et cetera, et cetera. This is what I mean by saying it's physics inspired, because as an OR guy, you wouldn't think like this, right? And then it turns out, when you run problems, and red is our gamma and in blue is Gurobi, in smaller problems, blue is better than red. But as problem becomes more, you can see how the red starts beating the blue, and the left axis is, by the way, log scale, right? So this is, so I'm not saying I'm going from exponential to polynomial. I'm just saying I'm going from bad exponential to less bad exponential. Again, a practical math, right? Similarly, you can see in quadratic semi-assignment problem, you can see in quadratic semi-assignment problem with the columns constraint. And what I really love is the cardinality Boolean problem, because the blue is Gurobi. Of course, sometimes it's much, much faster, than this. And sometimes obviously it's much, much slower because it's again log scale. But look at how consistent gamma is. Again, as a software guy, I want to press a button and get an answer in 1 second. Not that I get an answer sometimes in 0.01 seconds, and then sometimes it takes me 4 hours. See, that's not good software. Okay, I would rather get 1 second answer, most of the time. So there are some benefits, I think, of using this different approach. So David is going to be finishing up a paper comparing this also to many heuristics that are out there, because that's a more fair comparison. And our goal would be to have this paper ready by the end of the summer. Okay, so. And then maybe give talks about this in the fall. There are many applications that fit this, where f of x is messy, ax equal to b have integer constraints, and I've been collecting various instances, with different partners. One of the companies I'm working with is a hedge fund in New York, and I want to see if these methods are better than what they're doing. See, what I like about people in practice is they are doing something, right? They're not theoretical. I mean, the guy goes in a hedge fund, is a $2.5 billion hedge fund, $3.5 billion hedge fund is doing $2.5 billion of trade every day. Okay, the guy is doing something, right? All I'm saying is, if you tell me what you did yesterday, right? I can tell you what I would do with the same data, from yesterday morning, and we can see, would I give a different answer than you do, right? And would I give the answer faster than you do, right? And then it becomes, okay, maybe we should swap out what we're doing with what you're doing, Sridhar, right? And so I bring this up again because a fundamental difference between working with practice and writing papers is, in papers, they want you to compare it with an imagined optimal solution or some other heuristic, which is fine. But a practical person says, no, I'm doing something. You want me to do something else, show me that you're going to make me $100 million more a month or something like that, okay? I don't care if theoretically 400 more million can be done under some assumptions. If you can show me that I can make 100 million more a month, fine. I will hire some engineers or repurpose my engineers, and we'll swap out our current code with your code. So I want to bring this up again because many times there is a fundamental disconnect between what referees are looking for publishing a paper, which is fine, but the mentality and the mindset you need to go to practice. And as an academic capitalist, I think I've seen kind of the two ends. And sometimes when you're very, very good at writing papers, you don't make sense to the guy in practice, because the guy says, I don't care about all that. Just tell me how much better it is, for me, right? And show it on my data. Right, and so on and so forth. So I just want to bring it up because more and more of our community wants to do practical things, and I think part of it is the mindset that's needed to say, if you want somebody to change what they're doing, show them that it actually improves what they are doing. And again, without too much effort and risk and so on.
Sridhar, a quick question. You gave the example of a discrete deterministic problem, but for a hedge fund, you may have a continuous and stochastic problem. So are both equally applicable on a D wave?
Very good. The stochastic part is not a problem because expectation, if you is basically, you can qualify a simulation, or if you have right-hand sides that are random, the Graver basis actually doesn't depend on the right-hand side because it depends only on the kernel, for example, right? The continuous variable is an issue. And so we don't have good methods for continuous variables except through certain discretization, right? Because in the end, if you're going to go back into an Ising model, you have to make it a 0-1, through binary encoding and so on. So I don't consider stochastic to be the issue, but continuous would be an issue. And so what we're doing is discretizing it to say, tell me kind of the range are you going to move 0.1%, 0.2%? So basically what happens, without going into too many details, is they have a portfolio, they want to readjust their portfolio. Are you going to go up, go down, do nothing? Right? And then there's a range. They don't like move too much, right? So then I said, look, what if I tell you the answer is move 0.1, 0.2, 0.3, 0.4 up to 1.2 minus 1.2. If I give you that, is that enough for you? And then you say, yeah, fine, I will take care of it. That is, it doesn't have to be a fully continuous answer. It may be enough for them to say, fine. If you tell me these guys are moving up, these guys are moving down, this is by so much, we'll do some post-processing from you and take it from there, right? And so I think what they're looking for is adequate proof that the suggestions that we are going to be making are worth implementing. That's really what.
So on the stochastic side, do you have to keep calling it again and again to get a distribution? Supposing my output is a distribution as opposed to a 0-1 answer.
It depends on how we set it up. I mean, remember, I've already moved the objective function to an oracle call. So the oracle can just search through different chance constraints, if that's what you're looking for over there. And then on the right-hand side, if they're varying, then you should call each time because you need a feasible solution to that right-hand side. Okay. Kernel call can be only once.
Okay.
Right?
Yeah.
That's what happens.
Thank you.
Typically, in this hedge fund, they solve this problem in the morning and decide their movement in the day. So, right. So their interest is not that I'm faster than them. They just want to know, are you better than me?
Right. I know in London, in the city, because they have to do a lot of computations. So the speed is their primary motive to move to quantum computing.
Yeah, that is one application, but the application I'm doing here is not that.
Okay, yeah. So for a risk manager, for example, they want to know the VAR, has it changed or not, because the interest rates changed last night. And that's a huge computation if they're doing by simulation.
Right. So I think there's a big community looking to improve simulation of financial things using quantum. That's not what I'm doing because I'm actually optimizing the decision. Yeah. Okay. That's what IBM consultants would likely be doing with JP Morgan Chase and things like that. Okay. Remember, I'm only talking about my application, not necessarily all applications.
Yeah.
Right. Yeah. So I want to spend just a few minutes. I don't know if we're running out of time, George. You want me to take 5 minutes or stop or?
I'm happy to.
Yeah. Go ahead. Take 5 minutes. Yeah.
So a year and a half ago, I created a prize, named after myself, of course, and then said to IIT students, can you do a room temperature, non-classical computation used on available components that is semi-classical, right? Because there are papers being written about how Ising can be mimicked as a first order solution to oscillation based. Can you do it? If you go to my blog, you'll see a post called the 2020 Tayur Prize. You'll see 2 finalists. And if you click the link, you'll actually see the presentation. They built 2 machines and pressed the button and did the max cut and compared it with D-Wave and beat D-Wave. Okay, so undergrad students with less than $1,000 project can be D-Wave today, right? And so one of the things that people are doing, NVIDIA, Google, Fujitsu, they're saying, oh, okay, if that's what you want to do, if you want to solve an Ising type problem, you don't need to do all of this. We can do it through GPUs. We can do it through tensor processing units. We can take CMOS technology and build these things. Fujitsu said, oh, I can build a digital annealer. So what you're seeing on the market is physics-inspired computing, which is room temperature, which is coming in this size. So I have another block called pocket quantum computing. So my joke was, if these guys do it, we'll have a quantum computer in our iPhone, right? So here are the different people doing Ising solvers that are available today. They can see what the number of bits are, and once you've built a Cubo, Manmohan, you get all of them. It just cut paste their name and change the API, right? And so that's what Amazon's done. Amazon has gone to D-Wave, gone to Toshiba, gone to IonQ, blah, 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 and said, guys. We are not building a quantum computer. I'm just building a platform so that people like Sridhar can come on the platform, write Cubo once and go to D-Wave and go to Toshiba, okay? Or write quantum circuit once and go to IonQ or Rigetti. Okay, that's what Amazon Bracket is. Amazon Bracket is the platform that connects you to various quantum computers. And once you decide which, are you VHS or beta, a technology, then it just cut paste. Instead of calling it IonQ, you call Rigetti, and then calling D-Wave, you call Toshiba.
So I didn't understand. So do they have just some physics-inspired machine, or do they just hook up to somebody else's computer?
No, they hook up to IonQ, they hook up to D-Wave, they hook up to Rigetti. They hook up to the actual machine.
Okay.
Yeah. So this is what I used to teach in the class. So students actually wrote code, called D-Wave, and that was the homework.
Mm-hmm.
Yeah. So I want to summarize it here a little bit. So hopefully this talk gave you a sense of some vocabulary. You know what a qubit is. It is a superposition of 0 and 1. You have seen an Ising model. If you haven't heard of Ising before, you say, I now know Ising. Adiabatic quantum computing, right? Starting from a known Hamiltonian to the other one slowly. And solving problems using test sets, Graver being one of them, right? So hopefully, there was some new information there. Grover and Shor in the 1994, 1995, 1996, I think triggered this whole interest in practical quantum computing, although their work is very, very theoretical and high-class quantum computational theory. There are two types of hardware, broadly, the D-Wave type and the IBM type, right? One is the AQC, and the one is gate circuit. Quantum supremacy is the hype, but I believe quantum-inspired hybrid algorithms and physics-inspired classical algorithms are worth pursuing even today, and for certain class of problems can give you speed-ups because they take advantage of things that classical methods did not think about. There are many, many applications across the board. And I think the battle is on whether we need the super cooled qubits, right? Like Google and Rigetti, or can we get away with kind of room temperature? Okay. So I believe for our community, nonlinear integer programs can be a very good application basis, right? And I don't know how the 21st century will look like, but I'm hoping that, it'll be a little bit post-Turing, right?
So
then,
when you say nonlinear integer, you mean pure, nonlinear pure integer?
Correct. Correct. Because the discretization is still an issue.
Yeah. Actually, you made me realize that many real-world problems, including supply chain, actually have all discrete variables, but we linearize them because we are used to linear programming.
That's right. We actually go the other way. Yeah. Right.
So,
this is an opportunity to say, wait a minute. In fact, I gave this talk at some students here, and I said, what is the first thing they teach you? What is the first thing they teach you when you take an IP class? LP relaxation. And I'm like, stop it, please, stop it. Stop it. Stop it.
Yeah.
And people are like, oh, what do you mean, Professor? I said, there are Gomri groups. There is Graver test set. There are ways you never leave the lattice, my dear boys and girls. And, we have been teaching them this LP relaxation, branch and bound, this Agon thing. And I'm like, stop it. Stop it.
Sridhar, when you do nonlinear integer programming, what about time element here where you have unfolding stochastic processes and you have non-anticipative constraints? How do you handle all of that into this?
We have to see. I don't know. We have to see, right? I mean, I think the sense I'm trying to get here is not that this field is 10 years old and I'm summarizing it in this tutorial. Interestingly, I created this field. So a tutorial is usually given when a certain body of work has been created and somebody summarizes it and says, this is what is happening. To call this a tutorial is probably a bit incorrect. Maybe we should simply say an introduction to a new field, right? And so there are many, many problems. I mean, for example, one PhD student is thinking about, can continuous variables be handled without discretization? Can we separate the problem so that the discrete problems go to quantum, the continuous remain continuous, and create a different type of hybrid rather than having to discretize the continuous? I don't know. I mean, what I'm saying is, I don't know.
Yeah. I just realized another opportunity, because in the supply chain world, we split up supply chain planning from production planning, because production planning is discrete and supply chain planning, we don't need to.
In fact, this is what the Exxon Mobil guys noticed, hired David as an intern, and Exxon now has a quantum group, which is basically saying, why do we need to decompose if we don't have to decompose?
Oh.
Bingo, that's exactly what's happening. So suddenly, in fact, when I taught the class, there were people from Exxon and other companies also popping in to say, oh, what are you saying? I'm saying that the choices you have made in solving today are already assuming something. And I'm asking you to lift yourself from those assumptions. Here's an opportunity to say, wait a minute. Are you telling me I have this option? I can go back here? I say, yes. Now that you take 2 steps back and you can see the forest for the trees, maybe you will choose to do something else. That's exactly what I'm saying.
Yeah.
And in fact, why in God's name would somebody think about finding the kernel and doing conformal mapping? Unless I said, wait a minute, you're telling me I can find kernel elements in nanoseconds because of nature? And not having to write a completion algorithm which is triply exponential? Right? I mean, without which it would make no sense, actually. Right? So thank you. Here are some.
Has somebody made a pseudo quantum computer, a pseudo D-Wave? So I still write the code. It may take longer, obviously, but I don't have to change my code if I had a real quantum computer.
I believe there is a simulated bifurcation machine by Toshiba. Mm-hmm. And then Fujitsu Digital Annealer, I believe, I have not used Fujitsu, so I don't know. They would both say that they are simulating Ising on a classical architecture, right? A CMOS, chip, and the input would be QUBO, basically.
Okay.
So I think for our community, if we can start thinking in terms of different ways of decomposing, different ways of searching, different applications, then what remains classical, what needs to be non-classical, and then if you take the Ising approach, the non-classical will be through QUBO. That will be kind of the overarching framework.
Are these slides available on any of the sites?
You should see this actually on the GitHub slide. Did you see the GitHub page here?
Oh, the the Bernalde.ait?
Yeah.
Okay.
Yeah. So actually, if you go there, I gave a special lecture to IIT Madras. It's called lecture 12 or something, called Summary of the QUIP course. All the slides and my video are there, and I basically extracted this from there. So there is this and more, because there I had like 90 minutes to do it. So I don't think there's any slide here that is not in there. They could be a bit out of order here and there, but
Thank you.
the substantive slides are going to be there.
Yeah. This was definitely very eye-opening.
Well, thank you for coming. I hope it gave you a sense of what is going on. And part of what I want to do is to demystify quantum computing, right? There's nothing mystical about it. Even quantum mechanics, honestly, just shut up and compute, just use that as a mathematical framework because it works, and not make it as if, the Eastern mystics had the yin and yang and all that, right? So I always took a more Heisenberg view of the world, which is, look, man, I'm not saying this is how God was thinking, but this is what we can do with our brains right now. So can we go ahead with it, right? And so similarly, quantum computing, I take a very pragmatic approach and say, tell me the machines you're building. What are the inputs to those machines? What are their strengths and weaknesses? When can they do something that's very difficult for classical? And let me see what I can do now. And if and I'll wait to see what happens in 2 to 5 years.
Okay. Thank you very much.
Thank you for the introduction to quantum computing.
Yeah.
Well, did it meet the claims of the abstract? That at the end of the day, right? I mean, the abstract said you'll hear about Ising, you'll see some applications, there'll be hype versus reality, and you will leave knowing more about quantum computing than before you came in. Were they satisfied? I mean, that's the question.
For sure. I mean, I've just heard the terms, and it did seem like black magic. And what you said is actually practical, not black magic. And I think there'll be more and more hype as we go along, coming from IBM and Google, to make it even more of a black magic. And so this has been extremely helpful.
Yeah, one thing that I can say from experience is that the technology changes the way we view operations management, how we model and all that. I think this will fundamentally change how, like you said, how we are going to do planning, or how do we decide on facility location, because facility location now is a static problem, and the complexity itself make it not to include the important things that happens. So what I see is, when I was a PhD student, if you wrote something as a stochastic programming problem, it is doomed because nobody can solve it. So all we did was, all production planning problems are deterministic problems. That's all we could do. But things change, and that's why we need to hear more from Sridhar, is that how he visions the process operations management is going to change because of this technology coming along, and the advances are being made.
I mean, I would have never thought of Ising models and try to do an Ising solving algorithm, right? I mean, so to me, this has already given me a new way of looking at things than 25, 30 years of looking at papers written by our own community, right? I mean, sometimes finding something that is probably straightforward in another community can lead to remarkably different ways you look at yourself. Right, and so I think this could be one of those.
I appreciate what you said about, because my consulting experience has been, I even developed. They don't ask you to prove convergence or anything. They say, here's my data, run it, and show me how well it does. Right. The problem is cross-validation is the most important thing, but you cannot publish a paper because of that. No. So now what I'm looking at, even yesterday's tutorial, Max Chen was complaining that he has a nice algorithm that is implemented by JD.com, but he cannot have it published. So the question comes now, do we develop a theory that's going to be focused on the advantages that's going to come out in implementation? don't prove it's going to convert. Does there exist a theory focused on the cross-validation aspect? So I've been talking to Max and saying, can we do something along that line in terms of don't assume IID like we normally do, but does there exist sufficient characteristic of reality over which we can develop a theory? Move towards that, making it academically also publishable.
That's a good idea. Yeah. I mean, I think what the computational group of math programming has done is created benchmark problems and said, look, if you have a new algorithm, run it on these 12 problems and write down what you have done. Okay. Don't make up 12 random problems and say you are awesome. Okay. Beat this, right? And so I think you're taking it to the next level to say, that you can do that, but you also need something that says that algorithm with this kind of mathematical structure of the real problem is guaranteed to give a certain result, and that could be a very interesting bridge, I think, between actually solving a problem in industry and saying something meaningful about what it could do in industry. Yeah. I know we are way out of time, but I appreciate you guys inviting me, and hopefully, as I said, it's going to be on YouTube, right? So other people can watch it if there's.
Yes, it's going to be on YouTube. Okay, thank you, Sridhar.
Thank you very much. It was very
Thank you.
inspirational. Yes, well, bye.